Now in this lecture we shall learn that how we can calculate the seismic load for steel structures. So this is a theoretical example again to help us understand that how we can calculate the seismic loads as per the Australian standards with various parameters. So in the first example we shall be discussing about the seismic loads for the steel structures. So, first of all, let us assume that the structural system that we are having is the steel structure. And structural description is basically the special moment resisting frame. And we are assuming that it is fully ductile. So, as per that, we can select the structural performance factor also and structural ductility factor also. The number of levels assuming that we are having is 4. So this is how the steel structure can look, but obviously we do need to add the bracing so that we can classify it as a fully ductile. And so we can assume here that, although this is just a reference picture, so let us assume that we are having the cross bracings also here, or in some other frame we are having an eccentrically braced frame also as per the requirement. So, and the connections also are fully ductile. So we can assume that the structure that we are constructing of steel structure that is fully ductile. A number of levels, although in this reference picture there are 3, but in practical example we can assume as we have 4 number of levels. So and shall be 4. After that, we had already discussed in the earlier lecture that earthquake imposed action combination factor. So for imposed action we had discussed that we do need to apply this 60% for storage actions and 30% for the like a normal residential or normal office buildings where there is no asset storage. So this is the clause that I am discussing here. So in here you can see that for earthquake imposed combination factor it is 0.6 for the storage applications and it is 0.3 for other applications. So assuming it is for storage, we can take it as 0.6. So this is also clear that chi c can be taken as 0.6. After that, the height of the building can be assumed as height of the single floor or single level that can be assumed as 3.5 meter. So first of all, if you're talking about the gravity load, so for gravity load we can take it as, let us assume that G1 value is 1000 kilonewton and imposed action on level 1, that is at this particular level. The imposed action is 750 kN. The height is 3.5 meter, the one that we have discussed here. So seismic weight at level 1, that shall be G1, that is the 100 full value of the imposed action, that is 1000 plus 0.6 times 750. So this value comes out to be basically 1450 kN. So seismic weight at level 1 value is 1450 kN. Similarly, we can assume that imposed action at level 2, that is assuming it 2000 kN, and imposed action level 2, that also we can assume 750 kN. So height at level 2. So height at level 2 basically that shall not be the floor height, but it shall be from this particular ground level. So this is basically 7000 mm. So coming back to the formula here, so S2 shall be 7 meter, and again we shall be adding 2000 plus 0.6 into 750. So this value comes out to be 2450 kN. Similarly, the permanent action at level 3, again we assume that it is 2750. So height again for level 3, that shall be from this point to this point, that is H3, that shall be 10.5 meter, or we can say 10500 mm. So this value comes out again to be H3 as 10.5 and seismic weight again as 2000 plus 0.6 times 750. So this value again comes out to be 2450 kN. Similarly, permanent action at level 4. So let us assume G4 is 1250 and imposed action is 500. So 1250 plus 0.6 times 500. So this value again comes out to be 1550 kN, and height from the ground level here, that is up to this point to this point. So this comes out to be 14 meter. So these are the basic parameters. Total seismic weight shall be basically 1450 plus 2450 plus 2450 and plus 1550 kN. So this value comes out to be 7900 kN. Now let us assume the structure that we are going to construct here is basically is an Adelaide, and importance level BCA is, let us assume it is as 2. Annual probability of exceedance KP, that can be taken as per the building code of Australia table 3.1 as 1 by 1000. So probability factor KP, that we have already discussed that, as per the annual probability of exceedance, we can take the probability factor. So let us just go to that particular table. So in here we can see that as per the annual probability of exceedance as 1000, the probability factor Kp needs to be taken as 1.3. So that is the value that has been considered in this particular example. After that, hazard factor. So hazard factor can be simply taken from the table 3.2 or from the seismic map of the Australia also, and that is Z can be taken as 0.1. So the value of the Kp into Z, that is 1 into 1.3 is equal to 0.13. And as per the code, the minimum value of Kp Z, that needs to be taken as a 0.1. But in our case, it is 0.13. So it is higher only. After that, site subsoil type, that can be taken from the geotechnical report, and let us assume that it is deep or soft soil. So as per the code, if the soil under consideration is deep or soft soil, then the classification is basically class D. We can also take it as class DE. After that, earthquake design category. So earthquake design category, that can be taken from, we can say, table 2.1. So that also we have discussed in the lectures. That is, we can follow the clause 5.2 for that, clause 5.4, and we can proceed with the simple static analysis also. So after that, if we're discussing about the horizontal equivalent static forces, so structure form factor, and that can be taken from clause 6.2.3 as, we can say, 0.11. So this is the structure form factor, and that can be taken from this particular clause 6.2.3. So in here you can see that for moment resisting steel frame, the KT value is 0.11. And that shall help us in calculating the fundamental natural time period. So in our case, basically we can take that 1.25. KT can be taken as 0.11, and the height is basically 14 to the power 0.75. So let us just go back to the example here. So in here, what we have done is that 1.25 into KT has been taken as 0.11, and height has been taken as we can say 14 to the power 0.75. So this value comes out to be 0.995 second. After that, if we're talking about the natural period exponent, so that is also given in the code. That is, what we can do is that we can simply divide this natural period by 2 and add it with 0.75. So 0.995 divided with 2 plus 0.75 gives us 1.25 as the natural period exponent. Spectral shape factor CST. Now spectral shape factor can be taken as per this particular fundamental natural time period. So let us just open this table 6.4. So in here we can see that for deep or soft soil and natural period, we can say this as 0.995, approximately 1 second. So this value comes out to be as 1.98. So we can simply refer this value and consider CST as 1.99. So after the structural ductility factor, table 6.5a. So for the moment resisting steel frame fully ductile, mu and SP can be simply referred from the table 6.5a. So steel structure and we can say fully ductile eccentrically braced frame. So in here we can see that our mu is basically 4 and SP is 0.67. So these are the values that has been considered here. So mu has been considered as 4 and SP has been considered as 0.67. So horizontal equivalent static force acting at the base is basically Kp into Z into CST multiplied with SP divided by mu multiplied with the seismic total weight. So all of these values we have already calculated above. So if we want to repeat here, Kp we have calculated as 1.3 multiplied with Z, that is 0.1, multiplied with CST, that is 1.99, multiplied with SP. So SP has been considered as 0.67 divided with mu. So that is 4 and multiplied with the total seismic weight. So total seismic weight that is basically 7900 kN. So multiplying and calculating this, the value comes out to be 342.3 kilonewton. After that, we do need to divide this horizontal equivalent static force on the various multiple levels. So what we can do here is that summation of w into hk for all levels, that is basically summation value here, and wi into h1 to the power k, because we have 4 number of levels, so there shall be 4 summation terms. So w1 into h1 to the power k, w2 into h to the power k, plus w3 into h3 to the power k, plus w4 into h4 to the power k. So kf1 is basically, we can see here that w1 into h1 to the power k divided with summation of w into hk. So this value comes out to be 0.057. Similarly, if we want to calculate the horizontal equivalent static force acting at level 1, then we need to do is that we just need to multiply this with this. So 0.057 into 342.3. So this is the seismic force acting at level 1, that is 19.3 kilonewton. So this is the one that we have calculated here. So this is 19.3 kilonewton. After that, again, similarly we can do the summation math here also. That is w2 into s to the power k divided with the total, the one value that we have calculated here. So this value comes out to be 0.227. So 0.227 multiplied by 342.3 gives us 77.6. Similarly, we can calculate 128.7 also and 116.6 kilonewton also. So this is how we can calculate the horizontal equivalent static force acting at multiple levels as per the height, as per the permanent action load value, as per the the imposed action factor also. So just to repeat here, we have taken the annual probability of exceedance as per the building code of Australia as 1 by 1000. So as per the annual probability of exceedance, we have calculated the value of the KP. As per the location, that is Adelaide, we have calculated the hazard design factor. After that, as per the soil factor, we have calculated the Kp into Z and classified as the soil type as class DE and earthquake design category as 2. After that, we can calculate the horizontal equivalent static force by first of all calculating the fundamental natural time period of the structure, which is 1.25 into Kt into Sn to the power 0.75. So this value comes out to be 0.995. As per that, we can calculate the value of the CHT from spectral shape factor table 6.4, and mu and SP that are dependent on the type of the building and material of the building. So as we had assumed steel structure and fully ductile, so as per that, we can simply refer table 6.5a and find out the value of mu as 4 and SP as 0.67. So horizontal equivalent static force acting at the base can be calculated as 342.3 kilonewton, which needs to be divided in various levels. That is 4 number of levels. So multiplication factor has been calculated as 0.057, 0.227, 0.376 and 0.341, which when multiplied with this value gives us the horizontal equivalent static force acting as 19.3 kN on level 1, 77.6 kN acting on level 2, 128.7 kN acting on level 3 and 116.6 kN acting on level 4. So this is that is the basic first example. So in the next example we shall be discussing about the concrete structures.